Now, a mole is 6.02 times 10 to the 23rd of anything. It's a really big number. 10 to the 23rd is big. And usually what we say is a mole of molecules or a mole of atoms is 6.02 times 10 to the 23rd. And the reason why that number is so big is because atoms and molecules are really small. And so we can write this as a conversion factor, either 6.02 times 10 to the 23rd molecules or atoms per mole over moles, or we can flip it and write it as moles over 6.02 times 10 to the 23rd. Now, if you recall, when we were doing setups for conversions, anytime you have something over something, that's a conversion factor. So this actually can get you from molecules to moles and from moles to molecules or atoms. And so we use that. We use the mole and molecules anytime that we have atoms or molecules. So let me just copy this down again. 6.02 times 10 to the 23rd per mole. And we're going to use this when we see molecules or atoms. Okay, and we're going to have several conversion factors in this chapter, and we're going to have to know when are we going to use them, because if you use them when you don't need them, then it's not going to be right. And so we want to make sure we use these conversions, and here's our first one for this chapter, when we actually need them. And so we're going to use this when we see molecules or atoms. And so here's an example here. So how many molecules of CO2 is 0.409 mole CO2? Okay, and so this is the way we're going to do these problems in this chapter. I look at this problem, and I don't go straight for a setup. It's much easier if you just look at it and decide, what do I need to use? Because we're going to have bigger and more complicated problems. This is our first one, where we're going to have several conversion factors that we're going to need. So we need to make sure we have the right ones. And so what do we see here? I see the word, well, we drop this how back, and we'll say how many, just to keep my English right. Well, let's change color. Okay, and so I see how many molecules. And so that's our key phrase. When we say how many molecules, I know I'm going to need 6.02 times 10 to the 23rd molecules CO2 for every mole CO2. And notice how I added on the CO2. I didn't just say 6.02 times 10 to the 23rd, and I didn't just say 6.02 times 10 to the 23rd molecules. I went molecule CO2 for every mole CO2. And it's important to do this, because this is what we're doing here by adding this on here, is that's a tag, just like a name tag. That's so that we know what it is that we're talking about. Now, I know there's only one thing in this problem, and it's CO2, carbon dioxide, but that doesn't matter. We still need to tag everything. And so I don't see anything else up there other than molecules and moles. And so I do have a conversion factor to go from molecules to moles and moles to molecules. So now I can go ahead and set this up. And what does setup be? Well, we draw a line, draw another line, and of course we always start with the measured number. That always starts every problem, is the measured number. Now, what do we have up there that's measured? Well, our measured number is the 0.409 moles CO2. There it is. That's my measured number, because I actually had to go out and measure it. The conversions are not your measured numbers. Okay, always start with your measured number. And so we're going to go ahead and start with the measured number. And so we say 0.409 mole CO2. And if you remember when we set up problems previously, we always want to set up problems so that units cancel. And the units is moles CO2. So where do we have moles CO2? They're right here. And the mole CO2 just so happens to be on the bottom where we need it to be. So we copy it down. And so the moles CO2 goes down on the bottom. And the 6.02 times 10 to the 23rd molecules CO2 goes on the top. And that's so that mole CO2 cancels, and we're left with molecule CO2. Because what are we looking for? We are looking for molecules of CO2. Not to be confused with moles. Moles and molecules are not the same thing. So we go ahead and put this in our calculator. And you should do this on your calculator to make sure that you can do it. Okay? You need to be practicing. And so I put this in my calculator, 0.409 times 6.02, and I use a special EE key on my TI-84 Plus, and I get another big number, which is 2.46 times 10 to the 23rd. And this is, of course, molecules CO2. Now we can do another problem. Let's do another one. Let's do another example. So how about if I know how many molecules I have and I want to know how many moles that I have? Let's say I had 4.02 times 10 to the 24th atoms of chlorine. I want to know how many moles of chlorine is that? Okay, now we have atoms of chlorine. And I want to know how many moles that is. Well, once again, we're looking for keywords. And what do I see over here? I see atoms of chlorine, which means I'm going to need, and besides, we also see we have a pretty big number over here, which means I'm going to need, once again, 6.022 or 6.02 times 10 to the 23rd atoms chlorine for every mole chlorine. Because that's my key. That's my key to tell me that I need that conversion factor. And like I said, there are going to be more conversion factors. So we're starting with the simplest one. And that's all I need out of this problem. There's nothing else. I've got atoms and moles. Atoms and moles. And so sure enough, my conversion factor has atoms and moles. And we're going to draw a line. And we're going to draw another line. And we start with our measured number. Where's our measured number? It is right there. And so we say 4.02 times 10 to the 24th atoms chlorine. All right. Now, what do we need to put down as our next conversion factor? I need atoms chlorine so that they can cancel. And where do we see that? I see this right there. Atoms chlorine. It's on the top. And I need the atoms chlorine to be on the bottom. So I'm going to have to take this and flip it over to get the units on the bottom. And so if I do that, that puts the 6.02, and don't forget the exponent, times 10 to the 23rd atoms chlorine on the bottom. And that puts moles chlorine on the top. See, all I had to do was just flip it over to get the units on the bottom, so that units, atoms chlorine, cancels. And I'm left with moles chlorine, because that is what I'm looking for, is how many moles chlorine. So the unit that doesn't cancel is what we have. And so let's go ahead and put this in the calculator, and you should do that too, just to make sure you can understand how to put exponents into your calculator. And Let me go ahead and put that in there. So we're going to go 4.02 second EE to the 24th this time, divided by 6.02 to the 23rd, and I get 6.68. 6.68 mole chlorine. And so that's a lot of atoms of chlorine, but it's only 6.68 moles of chlorine. Moles allows you to have very large numbers of atoms, and it's something that you can work with. So at the end of the day, what are we doing here with our 6.02 times 10 to the 23rd per mole? We're using it to go between atoms and moles and moles and atoms. Now, it turns out, well, that's not terribly exciting, but it turns out that because of the way that we define this, let me write this down again, 6.02 times 10 to the 23rd per mole, because of the way that we define this, we can now get something that will relate mass to moles. Okay, now, it turns out that if you have 6.02 times 10 to the 23rd of carbon 14, then that will be equal to a mole, of course, of carbon 14. Pardon me, that's carbon 12. Excuse me, let me change that. Carbon 12, carbon 12. Okay, I was thinking about radiation. 6.02 times 10 to the 23rd of carbon 12, and a mole of carbon 12, this will actually be equal to 12.000, as many zeros as you want, of carbon 12. And you may say to yourself, well, why does that matter? Well, that's some grams. Why does that matter? If you look on the periodic table, you will see that carbon looks like this. It's got a 6 above it. Well, that means it has 12 protons. But if you look down below, it says 12.011. Well, because of the way we define that, that now means 12.011 grams carbon for every mole carbon. You see, when we're doing reactions and we want to know how much we're going to get or how much we need, well, what we do is we actually weigh things out. Usually we just put something on a scale, and it turns out that if you have 12.011 grams carbon, then you have 1 mole of carbon, which is a counted quantity, which means you have 6.02 times 10 to the 23rd carbon atoms. Now, the 12.01 represents a weighted average of all the isotopes. So this is an average of all the isotopes. And since carbon 12 is 99% of all the isotopes, it's pretty close to 12. And if you recall, you have 3 common isotopes for carbon, which is carbon 12, carbon 13, and carbon 14. Carbon 13 and 14 being radioactive. So naturally occurring carbon, the average is 12.011 grams of carbon for every mole of carbon. So doing this, this actually tells us, and we give this a special name, we call this the molar mass. We call this the molar mass of carbon. Okay, and if you look below all the elements on the periodic table, you'll see a number down below that, and that actually corresponds to the number of grams per mole. And that is much more interesting and useful than 6.02 times 10 to the 23rd per mole, which is Avogadro's number. But you need that to be able to get to that number in grams per mole below carbon. All right, so what are we going to do with this now? And so we have keywords. And so first off, let's go ahead and put the 6.02 times 10 to the 23rd over per mole. And this is whenever we see atoms or molecules. And we have a new one, which is grams per mole which is the molar mass. And we're going to use this when we see grams of anything. Okay, what that means is that anytime you see atoms or molecules in a problem, you're going to need 6.02 times 10 to the 23rd per mole. And also, if you see grams in the problem, then you know right away you're going to need the molar mass. Okay, now, an essential skill here is to calculate the molar mass of compounds. Now, we can get the elements we get straight off the periodic table. A compound has more than one atom, so we have to be able to add up all the atoms. And so let's start with something like aluminum oxide. This has 2 atoms of aluminum for every 3 atoms of oxygen. That's what the Al subscript 2 means. That's what the O3 subscript means. It means you have 2 aluminums and 3 oxygens. And I want to know, what's the molar mass? Okay, and for that you need the periodic table. Okay, so let's go ahead and pull up the periodic table, and we find aluminum, and we look underneath aluminum, and we see the number 26.982. Now, what we're going 26.982. So let's go ahead and write that down. 26.982 for aluminum. And we're going to round these for the purposes of our problems. We're not going to use all 5 digits. We're going to round this first off to 1 decimal. So the number I'm going to use is 27.0, and that's grams aluminum for every mole aluminum, making sure that we're tagging these. And I look on my periodic table for oxygen, and I see 15.999. 15.999. And we're going to round that to 1 decimal, and of course that would be 16.0 grams O, or oxygen, for every mole oxygen. Notice that I'm labeling everything. I'm labeling everything, and that's very important. So let's go ahead and find the molar mass. Well, if there's 2 aluminums, and that's times 27.0, and this is 3 oxygens, so we say 3 times 16.0, and of course we're getting the 2 is coming from here, and the 3 is coming from here, and a 27 and 16, those are the molar masses for the aluminum and the oxygen. And if we add these together, we say 2 times 27 plus 3 times 16, we get 102.0 grams, and this is for the compound aluminum oxide for every mole aluminum oxide. Okay, so now we have the molar mass for aluminum oxide. We can do the same sort of thing for, let's say oxygen gas. Oxygen gas is O2. That means you have 2 atoms of oxygen for every molecule of oxygen. And so in that case, well, oxygen is still 16.0 grams, what we say 2 times 16.0. Remember, we're rounding to 1 decimal, and that would be 32.0 grams oxygen for every mole oxygen. And finally, let's do another example. How about sodium chloride? What would be the molar mass for sodium chloride? And so we have sodium and chlorine, and I look on my periodic table for the molar mass of sodium, and it is 22.989770, and of course we're going to round that to 23.0 grams sodium for every mole sodium. And we look up chlorine, and we round it as well to 1 decimal place, and that's 35.5. grams chlorine for every mole chlorine. And now we can go ahead and figure out what is our molar mass for sodium chloride, table salt, and we say, well, there's 1 sodium times 23.0, and we say that's plus 1 chlorine times 35.5, and that is 58.5 grams sodium chloride for every mole sodium chloride. And so we can use the molar mass. Like I said earlier, we're going to do problems with the molar mass, and we're going to say we're going to use molar mass when we see grams of anything. And if we see number of atoms or molecules, we're going to use that. And we could use both. We could use both. So let me give you an example of just using molar mass. So let's just start a new page here. Okay, so we can say, well, how many grams is 0.516 mole aluminum oxide? Okay, and so I look here, and what do I see? How many grams is 0.516 moles aluminum oxide? I see, this is what we're looking for. How many grams? And of course, that's for aluminum oxide. Okay, that's how many grams is 0.516 moles aluminum oxide. There's only one thing up there, and that's for the aluminum oxide. And so I see grams. And what do I need? If I see grams, I need the molar mass for aluminum oxide. Okay, and so aluminum oxide, we already calculated it up. We need the molar mass for aluminum oxide, and that's 2 times 27.0 from the periodic table, 3 times 16.0 from the periodic table. Of course, 27 is for aluminum, the oxygen is 16. And if we do that, we get 102.0 grams aluminum oxide for every mole aluminum oxide. It's not just grams, it's grams per mole. That's the molar mass for aluminum oxide. And so I don't see anything else up there. I don't see atoms or molecules, so I don't need 6.02 times 10 to the 23rd. You only need that if you see atoms or molecules. And so now I can go ahead and set this up. I draw a line, draw another line, and I always start with my measured number. What's my measured number? It's right here. That's my measured number, boxed in green. And so we have 0.516 mole aluminum oxide. And once again, once we pull down everything that we need out of the problem, and we only need the molar mass for this problem because we only have grams going to moles, and moles go into grams, this is all we need, but we still have to look. We have to match. And so I see moles aluminum oxide in my measured number, and I know I'm going to need moles aluminum oxide down here. And so we're just going to take this number, and that's the one that has the moles aluminum oxide in it, and so that's 102.0 grams aluminum oxide. And I know I'm set up right because I can cancel everything, moles aluminum oxide, and I'm left with grams aluminum oxide. And so I pull out my calculator, I say 0.516 times 102, and I get 52.6 grams aluminum oxide. 52.6 grams aluminum oxide. Of course, I did sig figs for this. This is 3 sig figs over here. This is 4 sig figs over here. So our answer is whatever we have the least sig figs for, and that's 3 right there. Now, let's do another example. Let's tie everything together in one more example. And let's say that we wanted to know how many grams is, let's say, 4.29 times 10 to the 24th molecules CO2. Okay? Now, we look at this problem very carefully. And anywhere where we see grams, and why don't I, just to make this a little bit more clear, we say how many grams CO2 is 4.29 times 10 to the 24th molecule CO2. Okay, so anywhere I see grams, I need the molar mass, but look, I also have molecules, so I'm going to need both. So let's go ahead and let's get the molar mass of CO2 first, and that is 12.0 for the carbon. We look on our periodic table, plus it has 2 oxygens, and there's 16.0 piece on the periodic table, and that's 12 plus 2 times 16, and I get 44.0 grams CO2 for every mole CO2. But we're not finished here, because what do we see here? We see molecules CO2, so I know I need 6.02 times 10 to the 23rd molecules CO2 for every mole CO2. So you see, you have to go through and find everything that has the keys next to it. Anytime you see grams, you know you're going to need the molar mass. Anytime you see the number of molecules or atoms, you know you're going to need 6.02 times 10 to the 23rd of whatever it is per mole. And so now we have everything we need. Now we have 2 conversion factors in this problem now. And so I'm going to draw a much longer line. And once again, we're going to start with our measured number, and that's the 4.29 times 10 to the 24. So we go 4.29 times 10 to the 24th molecules, not to be confused with moles, it's molecules, CO2. And now it becomes a question of matching. We have to match. And what do I need to cancel? Well, I need to cancel the molecule CO2. Where do I see molecule CO2 in my conversions? I see it right there. Here's my molecule CO2. So molecule CO2 is on top, so I have to flip this over to get molecule CO2 on the bottom. And so I do that. So I say a mole of CO2 is 6.02 times 10 to the 23rd molecules CO2. And once we use up one of these conversion factors, go ahead and put a check mark through it. That way you don't accidentally reuse it. Because now we need to have moles CO2 cancel. We need moles CO2 down here, because we've already canceled molecule CO2. Now we've got to cancel mole CO2. Where do we see mole CO2 up here? Well, I see mole CO2 right there. And since it's already on the bottom, I don't have to flip over that conversion. That molar mass is a conversion factor. And so now I can just go ahead and copy down what I have up there, 44.0 grams CO2 for every mole CO2, and I'm done. And I cancel mole CO2, they cancel. And we're left with gram CO2, because that's what we're looking for. And so now we have something I can put in my calculator. I have to emphasize, don't try to memorize these setups. The best way to do it is just pull down what do you need, and then make sure everything cancels. And I'm putting in 4.29 times 10 to the 24th times 44, and then I'm going to divide by everything that's on the bottom. And there's only one thing on the bottom, that's 6.02 times 10 to the 23rd. And I get 313 grams CO2. So we can do this as long as you go through the problem and pull down what it is that you need. Then you can set up so that units cancel, and you'll get it right every time. So how about one more example? How many molecules O2 in 15.1 grams O2. Now this one you have to be very careful with. We have to go through, and first off, we're going to find our keywords, but you have to be very careful. It's a very common mistake that when we get the molar mass for O2, which is oxygen gas, to not put in the ×2. There's two of them there. That's what it means. The 2 on O2 means you have 2. So the molar mass of oxygen, and I know I need the molar mass because what do we see here? We see grams. Anytime you see grams, you need the molar mass. And what's the molar mass for oxygen? Well, that's 2 times 16.0, because there's 2 oxygens in oxygen gas. And the 16.0 comes from the periodic table, of course. 32.0 grams O2 for every mole O2. Now, looking through the problem, I see how many molecules O2, so I know I'm going to need 6.02 times 10 to the 23rd molecules O2 for every mole O2. So we're looking through our problem. We're always looking through our problem for keys. How many molecules? You know you're going to need 6.02 times 10 to the 23rd per mole. Grams of anything. You're going to need the molar mass of that thing. And there's only one thing up there with grams. We'll do problems later where we have more than 1 grams. And so now I can go ahead and set this up. And so I'm going to draw a long line and another line. Start with my measured number. Where's my measured number? It's right there. That's my measured number. And so we need 15.1 grams O2. And so now I'm just matching. Where do I see grams O2? That would be over here with the molar mass. There's grams O2. So I need to flip that over to get grams O2 on the bottom. And so we say a mole of O2 is 32.0 grams O2. I had to flip over the molar mass to get grams O2 on the bottom. And so now grams O2 has canceled. And now I look for, and make sure we check mark, and now I look for where do I see moles O2 that hasn't been used already. The check marked molar mass means I can't use it over again. And where do I see moles O2? I see it right there. And so since it's already on the bottom, I'll just go ahead and copy it down. And so we say 6.02 times 10 to the 23rd molecules O2 for every mole O2. And we're done. And moles O2 canceled, everything cancels, and we're left with molecules. So now I have something that I can put into my calculator. And so I say 15.1 times 6.02 to the 23rd, and then times 6.02, second exponent 23, and then that's divided by the 32. And you should be putting this in your calculator so that you can make sure that you know how to use your calculator. And I get 2.84. Change colors here. 2.84 times 10 to the 23rd molecules O2. Okay, so this is how everything is going to be calculated in this chapter. You're going to be calculating molar masses, and you're going to be using potentially Avogadro's number 6.02 times 10 to the 23rd, and you'll also use something called a mole ratio, which we'll do in the next presentation.